My name's Brenton Barmore. I did polylactic acid and accidentally managed to focus only on FDM and then sort of realized there's pretty much nothing else done with polylactic acid. At least that I could find. Well, and that is actually due to its very beneficial properties in FDM. It has an extremely low thermal expansion coefficient and it has a really, really low melt viscosity, so it's actually the best polymer to be using in an FDM printer. It's so easy to use compared to the others. It's also biocompatible. It's bioabsorbable, just like PMMA, and it's biodegradable, so it's used in a lot of green items. And it's actually food safe, so it's a very useful polymer. Man, this is missing a lot of my stuff, actually. So I had 3 images here. You mind if I just go download the new some material properties of an FDM part with 100% infill? Actually, I should have put and Michael on there. You can see that. Yeah, and MakerBot, yes. So some of these results come from MakerBot, and then just a general material property website. So you can see that the UTS is actually very similar, but to the typical bulk properties of PLA, but it can actually be a lot worse depending on the orientation of your infills and layers. And actually, MakerBot was useful and good several years ago before Stratasys bought them. They actually came to the conclusion that it is almost 100% related to how many outer layers you have. The infill has zero statistical effect on the overall strength of the part. And it's because the layers are not actually oriented in the direction of the way you're pulling it, so you just get a shearing effect that breaks everything apart. And shear strength is always much lower than, it's usually around half of what tensile strength is. So one of the suppliers is MakerGeeks. They sell a lot of stuff, and they actually sell polymer or certain filaments that they don't specifically make, but they sell a wide range. The first one is the only good picture I could find of a Ninja Flex style PLA that they sell. And it's so rubbery that like you can take the filament and stretch it to like 3 times its length. But it is very difficult to print. So they just add plasticizers to PLA to make it like that. The middle one is just a raw PLA. And they also sell this in a food grade. More recently they started selling it in food grade. And then the far right one is actually glow in the dark. So they add something that makes it glow in the dark. I don't know what though. They do that too. You can print mood rings now. And then Shaxson is, I'm just kind of giving a shout out to Shaxson because it's amazing. Cheapest filament you can buy. It's available at Fry's, so just up the road from us. And they only sell unfilled PLA and ABS, but they're dimensionally accurate down to, was it 5.05 millimeter? I had a case study. It was a biocompatible bone, actually, for a knee. Never been tried yet, because they're not sure how PLA will react in the body, but it shows the perfect modulus, which is actually a really important issue with bone. If you don't match the modulus, you'll actually cause whatever it is to kind of delaminate from it, and you'll have it break apart inside of a human, which is no good. So PLA, about 60%. Yeah, so high porosity to reach the same modulus as soft bone so that you can replace the actual joint. My first research study is the relevance of PEG in PLA-based blends for building 3D scaffolds, and actually in a focus on building scaffolding for a medical reason again. What they were actually only focused on the mechanical properties for this because they still have yet to get the kind of go-ahead to put anything in a human, like I was just saying. And here are some of the results. So a 40% offset for strain there, but it's because PLA is very flexible. So you can see that there is here. So this actually has an additive in it also. Let's see, my mouse comes up here. So this is 95% PLA, 5% PEG, 90%, 10% PEG. And then this one has 5% PEG, and then 50 weight percent. It's a ceramic. I forget what it is, but it's a bioabsorbable ceramic. So they wanted to see how adding something that is bioabsorbable would affect how fast it absorbs and its strength. So you can see in the first graph on the left that adding PEG significantly reduces the strength of the part, but it actually increases the dimensional accuracy, which I didn't include here, because it lowers the melt viscosity even further, and you can print at lower temperatures too, so you don't get as much thermal shrinkage. And on the right there, it is a graph of how long it took to lose, or time versus weight loss in a simulated body fluid. And you can actually see with adding PEG lowers or increases the speed at which weight loss occurs, because PEG is actually water soluble and will disappear very quickly. And then if it's just the PLA with a little bit additive, almost nothing happens over the course of 8 weeks. So they could get an idea of what you would need to make it biocompatible and how you could adjust its properties to fit the application that you're using it for. And then my second research study was much more low level. So it's the mechanical property of PLA, printed PLA parts in shear. And all they wanted to see was how process parameters affect the shear strength of FDM parts. So here's kind of a hard to read graph, but the gist of it is that the run number 3 actually has the highest strength at just over 50 MPa, and it has a very very low layer height, 100% infill, and they heat treated at 100 degrees Celsius to stress relieve it for 20 minutes, and it actually makes it like 20% stronger than all the other polymers. It does make it more brittle, but typically PLA is brittle depending on how fast you load it. And then you can see down on the bottom there is run 1, which interestingly enough has the lowest layer height and lowest infill, but wasn't heat treated. Is actually weaker than most of the other ones. They did a Takeuchi analysis, but I'm not too familiar with it, so I didn't include it. And those are my 2 references.